A presynaptic neuron releases a neurotransmitter into the synapse. The neurotransmitter then binds to receptors on the dendrites and opens ligand-gated channels that allow for sodium to travel down its gradient into the cell body. The resting membrane potential is negative 70 millivolts, and the sodium, being a cation, when it enters, it depolarizes the cell body. This is a graded response. So more neurotransmitter means more open channels, which means more sodium. Though we have another cation, potassium, leaving as the sodium enters, the latter is entering at a much faster rate. So the result is still depolarizing. When we reach threshold, which is negative 55 millivolts, it propagates an action potential, which happens right here at the axon hillock. All right, so this is an all or nothing response. So if we do not reach negative 55 millivolts, no gates are going to open. These are voltage gated channels. So no negative 55, no gates. No gates, no action potential. So when those voltage gated channels open, sodium is going to flood the cell. It's going to depolarize so fast that it actually reaches positive 30. When it reaches positive 30, those sodium channels are going to close. But potassium ones are going to open. So sodium's going to be trapped in here, and our potassium is going to be leaving, kind of the reverse of where we're at when we are at resting membrane potential. So sodium's entering, and as it's entering, this area here, for instance, reaches negative 55. And then this area, then this area. So it kind of continues down in a wavelength fashion. So as this area depolarizes, this area depolarizes. And as it becomes super depolarized, the potassium channels open here, and then they open here, and then they open here. So it's just like a giant wave. It's like dominoes, essentially. So as it continues all the way down to the terminal end of the axon, the voltage-gated channels for calcium are actually... voltage-gated calcium channels down here are going to open up. When calcium enters, it's going to trigger this neurotransmitter to be released via exocytosis into this synapse. So let's get a better look, though, at what's happening on this handy-dandy chart. Okay, so we are at resting membrane potential, negative 70. Those channels are going to open up when the neurotransmitter binds, which is going to slowly depolarize us. We get to negative 55. And this is the point during depolarization, which is this half of the graph. This is the point where those floodgates open and sodium just goes crazy. Sodium, sodium, sodium. This is where the sodium channels close, but potassium ones open. The potassium ones, though, allow potassium to leave. So this is us repolarizing all here. Sodium's inside, potassium's going outside. This is us repolarizing. We get down here, we are hyperpolarized. Potassium did such a good job in repolarizing that it actually hyperpolarized it. So those sodium channels here aren't going to reopen until we're at resting membrane potential. So we have to rely on the sodium-potassium pumps to work on getting us back to our normal mix of sodium, so more sodium on the outside and more potassium on the inside. Then we will reach resting membrane potential again.